Section 4.7 is on exhaustion by compact sets. So I'll actually just jump ahead to exhaustion for a second, then I'll come back to the topological groups to finish. So I won't try to tell you, I'm not going to try to really present the things in 4.7. I'll ask you to read it. I just want to talk to you about the idea of 4.7, okay? And if we can find a homework problem to work on it later, we'll do that. Oh, hey, I'm supposed to give you guys homework problems, aren't I? Hey, you guys are supposed to give me the rest of the stuff that you're going to do.
Well, now that we're done with compact, we can finish it.
Oh, okay, okay. Oh, I understand. Oh. You shouldn't wait for me. You don't want to wait. You don't wait for me. But okay. I will allow it. Let's see here. Okay, so definition. This is section 4.7. Again, we'll go back to 4.6 here in a second. So I'll try to wrap this stuff up today as best as I can. So section 4.7, exhaustions by compact sets. This is part of the complex analysis canon, which I kind of failed to cover properly in the course. There are theorems about basically this idea in terms of approximating things with polynomials that are basically built over this concept. And well, if we had a graduate course in complex analysis, I would feel obliged. I mean, I would feel obligated to cover it and try to explain it, but it is kind of beyond the pale for the undergraduate course. So, exhaustion by compact sets. You have topological space X. All right. And a sequence of compact subspaces. The sequence of compact subspaces, call it Kn, such that n is an n. That may or may not include 0, depending on who's listening, such that, it doesn't really matter, right? 1 Kn is a subset of the interior of Kn plus 1 for any n, and 2, the union over n of Kn is equal to x. This is an exhaustion by compact sets of a topological space. So let's see here. I mean, we can draw some examples of this, like the plane. So you want like a sequence of compact subspaces that are nested in this sort of natural way. I think. So we do like. Yeah, I think that's the standard example to look at here, like this. So this would be like Kn is equal to f inverse of n, where f of x comma y is equal to x squared plus y squared, right? So those are closed, hence compact subsets of the plane, because it's the inverse image of this continuous mapping of this closed set n, right? And they're nested, right? Like K1. Oh, that's not right. Not what I want. No. That's just a circle. That's not what I want at all. It needs to be more than that. That's not enough. I was trying to be clever, but I just managed to be dumb. This is not. I mean, look. You can cover every point on the plane is clearly on some circle of a square integer radius. Yes. No. Oh, I guess they're not. It's 1 and then root 2, and then anyway, I'm just dumb. Yeah, sorry. We want disks. Fine. I guess the set builder notation should be used to build sets. It's what it's for. You ever heard this guy's called set builder?
No.
It's a set builder notation. No? I don't say this too much, but I should. I mean, this is the set builder notation, right?
Yeah.
Some books call it roster notation or something, but I don't know why.
We covered that the first day of abstract one.
Oh yeah?
Seems unnecessary.
Yeah.
If you're that far into math, you should know what a set is.
I cover it the first or second day in calculus one. And I think it helps people to drop my course. I'm pretty sure it's part of it.
That?
So here, I don't know. People fear what they haven't seen before. You know?
Squiggly brackets, that must be.
Yeah, I know. So there's K1, and then of course, what's the interior? Like,
It's going to be, what's a strict inequality?
so of course Kn plus 1, the interior is like this. That would be like K2 interior would be, you know. Okay. Including the K1. So, clearly fits the bill, right? And then it covers the whole plane. You keep going and going. So there's an exhaustion of the plane by compact sets, disks. Now what he does in example 4.64 is non-trivial. He shows that R2 isn't homeomorphic to R2 with the origin removed. He's going to show that R2 is not homeomorphic to R2 with the origin removed.
Isn't that kind of like easy to see though? I mean like visually, like non-proof wise, I mean like, because it's like looking at like a plate and a donut.
Yes, now you know that because we have talked about higher notions of topology like
Yeah.
loops and homotopy and those things.
Yeah.
But you got to put yourself. You got to think. Put yourself here. Like in this book where we are, we have none of those machine. We have none of that machinery. All we have is like open sets, connected. I mean, they're both connected,
Yeah. Yeah.
right? Like
Yeah, of
connectedness
course.
is no help, right? These are. I mean, they're both connected. Neither's compact. That's not really directly a help.
Mhm.
You're exactly right. If we study the structure of loops and prove that like loops being some sort of topological construction, then that gives us a way to detect the difference with loops. But we don't have that yet.
Okay.
But that is
Sorry.
completely legitimate comment. I mean, totally, I agree with that. I think that's the mature and right way to think about it. So this is an example. This one way to look at this example 4.64 Minetti is just like how horrible it is to attack questions that are actually homotopy questions, really,
Mhm.
using non-homotopy methods. It's quite awful. But he has this. He argues by contradiction. If suppose there was a homeomorphism between the plane and the punctured plane,
Mhm.
and he studies this exhaustion that we're talking about here, and he comes to a contradiction in about a half page or so. But I won't go through it. You can read it, but you can use this exhaustion by compact sets to obtain a contradiction between those two things. By the way, this is probably more important than that. If you take a topological space, like in this case X, right? If you take a topological space X, right? And then you remove one point, right? Just remove that point, like that point X or whatever, right? Then you can say X hat is equal to X union with infinity. No, that's not the right thing to say. I'm sorry. No. I'm what? He says take a topological space X and a point infinity not belonging to X. All right. Then X union infinity, you can construct just symbolic, being attached to the point in infinity to x. And you consider the topology. The topology that you look at is A, such that A is an element of the given topology. Silence, woman. The given topology on X, unioned with X hat minus K, such that K is closed. Closed and compact in X. So I mean, the idea is you take the space you're given, remove a point, right, and then you attach infinity. So another way of saying this is you take that point that you're removing and put it at infinity. Kind of the same, it's just a different way of looking at the same animal. Anyway, with this new topology, the resulting topological space X hat is compact. This is called the one-point compactification of the space. So you can, in some sense, like, take a given topological space and just make it into a corresponding compact topological space in this way. This is known as the one-point compactification or the Alexandrov compactification. And he's like, proposition retaining the previous notation, X hat is Hausdorff if and only if X is Hausdorff and every point in X has a compact neighborhood. So, for example, this gives us a proof that the Poincare sphere, which is, by the way, the one-point compactification of the complex plane, the Poincare sphere, basically you're taking, so the complex plane, of course, is not compact, but if you add infinity to it, it gets to be compact. So an example of this construction is the Poincare sphere and the, say, the extended complex plane, if you like. But anyway, that's, I think, it's an interesting section. It's really quite, it's a little bit removed from the other things we're talking about at the moment. But both of those topics, the exhaustion by compact sets and also the notion of one-point compactification. I think you'll learn much more about that in your next course in topology if you take another one. All right, so that brings us back to section 4.6, which is on topological groups, which, believe it or not, I think I can do justice to in about 10 minutes. Is that okay? Do I have 10 minutes? Mm-hmm. Okay. All right, so what is a topological group?
A group object in the category of topological spaces.
Good answer. Algebra.
You and your words. Section 4.6. 4.6 topological groups. I think I agree with Nathan. I think I agree with him. A topological group is what it sounds like. I mean, it is a group in which the group operations are continuous mappings. And the group, let's call it G, with respect to G, well, let's say G's topology. So I guess I kind of buried the lead. Topological group is a topological space, which is also a group. And the group operations are continuous.
Is it the same thing as a Lie group?
Well, the difference between a topological group and a Lie group is there's no just continuous. So the difference with Lie group is we replace continuous with smooth. So that's more structure. There are things which are topological groups which are not Lie groups. But I think all the examples I'm about to show you, they're Lie groups. Yeah. Because these are matrix examples. So basically, you have, G cross G to G. That's the multiplication mapping M, right? to like multiplication of xy is equal to xy as our typical juxtaposition notation. Well, that has to be a continuous mapping from the product of G and G to G. We know what that means now because we talked about the product topology. So, and also the inverse mapping, right, which is G maps to G. Let's say inverse, I don't know, better notation, inverse of x is x inverse, right? I mean, that's whatever. That has to be also a continuous mapping. Now, it's pretty cool because you automatically, in this context, you automatically get some really, really neat mappings, homeomorphisms, actually. So, if you define left multiplication by h, all right, and left multiplication by h of x, how's that defined? Well, that's defined to be hx. Okay, and that's for x and g. If you freeze one of the entries, if I freeze one of the entries, and I let the other one vary, that's a restriction. A restriction of a continuous map is still continuous. Consequently, L sub h is a continuous mapping from G to G. In fact, it's not just that. In fact, it's a homeomorphism. Every left multiplication map is a homeomorphism of the topological group to itself. Because you can easily show it's invertible, because L of H inverse, which exists because G is a group, everything has an inverse, right? So this, it's easiest to show that this composed with this is just the identity on the group, right? Which shows it's invertible, and by the way, its inverse function is continuous for the same reason that the forward mapping is continuous. So you have an invertible mapping with continuous inverse. In other words, it's a homeomorphism. So the left multiplication maps are homeomorphisms of the group to itself. By the way, this is not at all surprising. Right multiplication by h, xh, same song and dance. All right. What's the relation between left and right multiplications? What if I have like L, let's say Lx, Ry, and I say take that times z. What does that give me? I get what? I get Lx of zy, and that's x of zy. Let's see here. What happens if I take r y of Lx of z? What do I get? Right. Or another way to say that is that to say that the left and right mappings commute for every pair x comma y in the group is tantamount. Right. So we can capture associativity of the group in terms of commutivity of the left and right mappings. Which is interesting. But I don't think that's in here. I'm just messing around. Sorry. Let's see here. For any G and H in a topological group, there exists a homeomorphism, phi, such that phi of G is equal to H. Okay, can you guys prove that? Here's the group. G, here's your point G, here's your point H. We want to find a homeomorphism, phi, such that phi of G is equal to H. Can you guys tell me how to construct? What's the formula for phi?
LH composed with LG inverse.
So phi is equal to LH composed with what?
LG inverse.
LG inverse. Let's see here if I believe you. So let's see here, we take phi of G, that's LH, and then we've got LG inverse of G. All right, so that gives me LH of G inverse G, which gives me LH of E, or the identity, whatever you want to use for the neutral element in the group, which is H. Very nice. Yeah. So the way to think about what Daniel's answer just gave me geometrically is like this. Here's the identity, right? So what you're doing is you're traveling from G over to the identity by left multiplication by G inverse. Because that to get from E to G, you go left multiplication by G. So to go the other way, you do left multiplication by G inverse. And then to get down to here, you do left multiplication by H. And that's why you have this formula. It's just traveling to the identity and back out again. That's how to understand it geometrically. Topological groups are fun. Groups are fun, right? Well, I got about 2 pages of results to tell you, and I don't want to hurry it, so I'm going to put that off until Friday, and then it won't take us more than about 10 minutes probably to wrap this up, and then we'll go from there into Chapter 5, Topological Quotients. That's where it really gets kind of abstract. but well, I don't know, we'll finally get some of the more interesting examples of manifolds, like projective spaces and such. At some point, I will try to come back to manifolds. Now that we have topology, we can talk about what a manifold really is. So at some point, I'll try to work that in this semester. I think we should talk about that. Since we have topology now, we can actually talk about what a manifold is really, as opposed to my just kind of ad hoc blah, blah, blah last semester.